Okay, we are going to look today at the differentiation of trig functions. And if you remember, one of the things yesterday that I showed you is we graphed. You can actually graph the numerical derivative. So what you want to do is set up your y1. I graphed the derivative of sine x. Remember that when you, instead of plugging in a value here, let me just show on this last spot here, instead of plugging in a number that you would normally do, you just plug in an x. So if I hit graph, remember you had to be in radians. If I hit graph, we got this picture, and it's kind of slow when it graphs it because it's going through the process of calculating the derivative or approximating it, and so it's a little bit slow. But remember we talked about how the derivative of sine x, and remember, hopefully you recognize this curve, that this is actually the cosine curve. So the derivative of sine is cosine. So what I want to do now is take a look at the derivative of cosine. So I already typed it in. I'm just going to go down and select this. Same thing down here, I have typed in an x there at the end. So if I graph this, okay, so think a minute what that looks like. It goes through 0, 0, which is what the sine curve does, but notice that it is going down first. From 0 to pi over 2, it is going down instead of going up. So what that means is that's reflected over the x-axis, so we end up with negative sine x. So those are our two basic building blocks that we're going to use for differentiation of trig functions. So then what about tangent, the derivative of tangent x with respect to x? Well, I'm going to start this by recalling that tangent is sine x over cosine x, which means I can do the derivative of this quotient, where this is u and this is v. So u prime, the derivative of sine is cosine, and v prime, the derivative of cosine, is negative sine. So then using the quotient rule, I get that the derivative of tangent is, so it's u prime v, so it's cosine x times cosine x minus uv prime, so sine x times negative sine x, all over v squared, so it would be cosine squared x. Okay, hopefully so far so good. Simplifying this, we get cosine squared x minus a negative sine squared, so I'm going to have plus sine squared x all over cosine squared x. Hopefully you remember a very basic trig identity, cosine squared x plus sine squared x, the Pythagorean identity. So the numerator equals 1 over cosine squared x, and this is the reciprocal, so this would be secant squared x. So the derivative of tangent is secant squared x, and we just proved it by using the derivatives for sine and cosine. Now if you look at the packet that I gave you on the second page, I'm skipping over that first page, here were your two basic definitions that you absolutely have to know. You must memorize these. And then down here they show you the proofs. This is what we just kind of did. The derivative of tangent is secant squared x. The derivative of cosecant x, you can kind of follow through that proof. And here's what the derivative is. So we have now we have all 6 trig identity or trig functions. We have their derivatives, and here they're all summarized for you on that next table. You will need to know these. Remember, on the AP calculus test there is no formula sheet, so you will need to know these. So now let's do some examples. Now we're still going to have to use all the same rules for the product rule, quotient rule, the power rule, chain rule, all of those apply. So here, part A, you can kind of find that on your packet. So we're going to take the derivative, so y prime equals, this is just like 2 times f of x. So then my derivative is just 2 times the derivative of sine x. Remember, the derivative of sine x is cosine x. So my answer is 2 cosine x. That's the derivative of 2 sine x. Now, this is a little different. Sine 2x, you can't treat, this is not raised to the second power or anything like that. Now, we have some trig identities, and that might be something too. You might want to, or maybe when we're at class, I'll print something off for you of a trig identity sheet, because you are going to want to use a trig identity for that. Okay, so sine 2x is equal to 2 sine x cosine x. So then if you were taking the derivative of this now, you would have to use the product rule. So we would get y equals, you can actually do the 2, kind of keep it separate, and then do the product rule. So it's going to be u prime v, so it's the derivative of sine, which is cosine x, times cosine x. That'd be the u prime v, plus u v prime, which this is going to be negative sine x. So we get 2 times cosine squared x minus sine squared x. And this happens to also be a trig identity, which is, oh, sorry, this is y prime, which is cosine 2x. And those, again, you might have to brush up on those trig identities. Okay, so our next problem actually is going to be real simple then, because it's 2 times, my derivative is just going to be 2 times the derivative of sine 2x, which we just got done doing. So then my answer is going to be 2 times what I got in the previous problem, so 4 cosine 2x. All right, now on this next one, remember that sine squared x, think of it this way. It's sine x squared. And so anytime you have a trig function raised to a power like that, you probably are going to want to rewrite it this way because it's easier to think about it. You've got the chain rule situation going on here because we have an outside function, which is something squared, and we have an inside function, which is sine x. So the derivative, using the power rule, I'm going to have 2 sine x to the first power, so the inside left unchanged, times the derivative of the inside, which is sine x. So I get 2 times sine x times cosine x, which, remember, I can simplify and say that that's sine 2x. Now, you wouldn't have to simplify that. If you were doing a problem and you left your answer like that, that's okay. It's just that there will be some instances where knowing these, the double angle formulas, will be helpful to you. Okay, on this one, I'm going to start by rewriting this as sine 2x, and this whole thing is squared. So when I do the derivative, I'm going to have to use the chain rule, so it's going to be 2 sine 2x, so that's the inside left unchanged, times the derivative of what's inside. And if you look back at part B that we already did, I'm not going to redo this, I'm just going to recopy it. It was 2 cosine 2x. So then I can just simplify this and say it's 4 times sine 2x times cosine 2x. Okay, going to kind of make a leap here. And remember when I said that sine 2x equals 2 sine x cosine x was an identity, then I can rephrase this. And it would be okay, again, it would be okay if you left it like this, but I could say that this is 2, let's see, hold on a second. Okay, it's going to be 2 sine 4x. And I was using this. You might want to pause that and think about that for a little bit. Otherwise, you can ask me about it next time we have class. Okay, on the next one, I'm going to rewrite this as sine of x to the 1/2 power. So then y prime, okay, it's going to be, on this one actually, well, I have an inside function and an outside function. So when I do the derivative of the outside function is cosine x to the 1/2, or the square root of x, with the inside left unchanged, times the derivative of the inside function, which is 1/2 x to the negative 1/2. So I end up with, let's write it as cosine square root of x. I'm going to put the 2 in the bottom, and since this is a negative exponent, it's going to be the square root of x in the denominator. So that's y prime.